Hey guys, welcome back. We're back in the shop. We're in front of the robo drill. Today we're going to go over a situation that I think is pretty standard for most machine shops that have been in business for X amount of period of time, right? We were doing a job, we were making it one way. We now have a new machine. There's been design changes. So now we're going to kind of cover and talk about the advantages of staying current with technology.
We're not your technology.
Right? Growing, trying to stay with the times, implement better processes to make that part more efficient. So this is a part we've been making. The OEM original part was made out of a plastic, right? It was like for a food grade application. It's being used for an application that's no longer food grade, blah, blah, blah. All these details and reasons as to why that part was failing, right? So then we reverse engineered that part. We made some design changes so that we could machine it efficiently and cheaply for our client and try to stay competitive, right? Because we knew that going to an aluminum part from a plastic injection molding part, that there was going to be a cost increase, right? And then so that's part of running a company, doing that stuff. It's like
a company that our clients can trust.
Explaining to them the value and then allowing you to make some test parts for them to run. So they start figuring, okay, well, if the part was $5 and now we're paying $10, but we're getting 3 times the life, okay, hey, that makes sense, right? And so that's part of that sale. That's part of the time frame that the lag that it takes to go from like maybe prototypes to a production run, right? So we created this part to where as we machined them, we were never machining a top and a bottom or a part A and a part B, right? The way that we machined them was it's a mirrored part. So now we don't have to keep track internally like, hey, did we make 200 lefts and 200 rights or 200 tops, 200 bottoms? So we did it that way. We also did it that way because at the time we only had the 4th axis on the hard hinge. And so we needed to make the part as simple as possible to keep price points down and all of that. So long story short, hey, they liked them. We built a bunch of them. Everybody realized and saw the cost savings of going with our part, even though it was more expensive because it was outlasting the plastic parts, less downtime, all of that. So then fast forward, they go, hey, we love it, but we want the bolts to drop in from the top more like the original OEM parts that we were using. Well, then of course, now we have a top and now we have a bottom part and it becomes more complicated. I guess something to note is it was basically taking us almost 55 minutes per part to make. It was taking a while on our 4th axis. It's a slow machine, slow rapids. I only ever ran that machine at a max of 7,500 RPMs. It's a 8K spindle. So now we're gonna hop over into Fusion. We're gonna go over the new part and we're gonna talk about why we designed certain features to now be better or more advantageous for the robo-drill. So the whole idea here was let's build this part as one and done. So we can obviously, in a 5th axis machine, we can get to this side, we can flip it, we can get from here, 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 here. We can get to everything except this bottom surface. And that's when we decided to go with a slitting saw to slit this part off as a one and done. We did some cool stuff here. We used some flat bottom drills, really went ripping, right? We used a really cool PH horn saw to get underneath and do things. And as you see here, right, in green is the finished part. And then we angle across, so you'll see that we actually cut in. So now we've left one 10,000ths thick tab. We're leaving one 10,000ths thick tab on the back side, and we leave the 3rd little tab right there, right? So the stock shows it fairly well. And I do one more little deeper thing right there. So the question is, hey, is this slitting saw going to be good enough? Is the part going to be parallel, square enough, all of those other things for the application, the tolerances that we're trying to live in? And we'll shoot over to the mill, we'll make it, and we'll decide. So now that we kind of talked about it over there in Fusion, we simulated it in Complete, now we're going to come over here. So something you guys have been asking for is people wanted to see the more nitty gritty, right, of the actual Haberly automated system, pallet pool system. So I'm going to show calling in a pallet for the first part. So our machine's ready. There's no pallet there. It's very simple. We go right here. It's a touch screen. You can either type here, you can type here, type wherever you want. So we're going to call in pallet 901. We're going to hit input. We're going to click pallet to clamping system. It's in MDI mode. It automatically calls up that code, kind of prompts us, tells us what's happening so that we know. We hit the green button. This is where the robot is going to come around. The robot's going to come in. It's going to grab the first pallet, which in this case is pallet 901. So materials in the machine. We're going to go over to memory. We're going to move through some of these tabs. So program 2000, that's what we're calling it. We're going to hit reset like a million times, like every machinist does. Just to be safe, everything's here. We're at 25% rapids. We're going to hit go. We're not going to probe. We've already probed. We've already established our workplace coordinates. It's going to come in and start machining this part. You can see that I have the coolant pressure of a 1998 Haas that's been neglected for 10 years. So it's kind of a bummer, but we're working on it. The struggle with filming a part is, it's a struggle. You know, it's hard to catch the angles. It's hard to even relay the speed of the machine, the sound. Right now, you guys are hearing the exhaust fan, you're hearing the machine, you're hearing the coolant pumps. The spindle is the most quiet part of this machine. If we just turn the spindle up to 20,000 RPM, you wouldn't even hear the machine. Right now, we're going to run some finish passes, so this isn't as loud or messy. All right, guys, the part's made. So now I'm going to go in there. I'm going to blow the part off. We're going to have the robot pull the part out of the machine, and then we're going to take a look at it. Safety first. All right, guys, so we made the part, and in a perfect world, I'd love to tell you that this machine is running lights out and that it's doing all this handshaking automatically, and it's not. And the only reason it's not is because of our coolant tank. As you saw in some of these other previous clips in the video, the coolant flow is real bad, right? It's not ideal. So we're working on remedying that issue. Like I said in other videos, this was a custom tank. It's a prototype. So we kind of missed the mark a little bit, but we're gonna dial it in. I hope to have like good information soon for you guys about what we're doing. So we called in pallet 901 earlier. We just simply hit empty clamping point, again, MDI. There's the code. We hit the green button. The machine's automatically gonna move to the location that it needs to be for the robot location. Orients it correctly in the 5th axis. Take a look at this part. Okay, so here's our part. I'm gonna go ahead and pull it out of the vise. Okay, so kind of like we saw in Complete and while it was machining, it just has these 3 little 10,000ths tabs. And even though individually those tabs are really weak because it's 3 points of contact, right? Triangle being one of the strongest shapes in nature, you're not getting this thing off. So I'm gonna take it over to the bandsaw real quick and I'm gonna cut the tabs off and I'll be right back. So we're getting close to automation, lights out, running, right? As soon as the coolant tank gets all figured out and squared in. Just to kind of give you an example, right? There's 120 pounds of aluminum loaded up in this machine at 2 pounds each, right? They're just shy of 2 pounds each block of aluminum, 60 parts. At 15 minutes of runtime, 20 minutes with like a wash down from chip to chip with the robot loading and unloading, you're looking at a 20-hour cycle time right here in this tight little compact package. So kind of discussing the intricacies of a one and done part, right? Obviously, I still had to lob it off on the bandsaw real quick, and you'll see that it's kind of, the surface finish looks different, right? And obviously it's different because it is. compared to this side, which was machined with an end mill, and that side with the slitting saw. The only thing that you really see on the slitting saw is at the very beginning and at the very end is where it's the worst. You get a little dig, right? And so there's a few things that I can do to kind of try to chase that and remedy it. And I'm gonna work on it. This part's still kind of being a prototype runoff. So, but what the client's gonna see, right, and what my client knows and we've already discussed, is after tumbling, all you can really see is that one corner. And then you gotta figure once it's hard anodized and it's dark, like this, it's gonna hide all of those little imperfections. And because this part just gets sandwiched between two snap rings on a square shaft, it's a floating sprocket, essentially, right? So it can move and it's gonna hit the chain. So the only real tight tolerance on this part, obviously the pins have to line up, have to locate within reason. We made a custom go, no-go gauge. So we have our go gauge here that we run through here, and it runs right through there, and I can barely get it to slide through there, right? So after hard anode, that takes into account the hard anode buildup and all of that. This is the no-go gauge, which can't start, and if it does, then the part would be too loose, and we would scrap it. So with this robo drill and the tight tolerances, running it through a good hour-long warm-up program, this just runs all day, every day, and we hit those tolerances. Hey guys, thanks for hanging out in my super messy shop today. I appreciate you guys. The next video is gonna be part B, which is the bottom of this part. That's where we're gonna get into some nerdy stuff. Chris from Zapatini Consulting, he's writing us a super sick macro. The boys from DSI helped us do a program in Fusion with some broaching, and it's gonna be super slick and it's gonna be nerdy, and I think you guys are gonna love it. And until then, thanks guys, I'm just happy to be here. See ya.